subfactors, tensor categories, and conformal field theory.
Okay. So I thank the organizer for the invitation to come here. I'm very glad to be here at the Newton Institute for the first time. So basically, I'd like to talk about the relations between subfactor theory and conformal field theory. So, conformal field theory is a physical theory, which is a kind of quantum field theory. So, if you look at the setting of quantum field theory from a naive viewpoint, I think there is no a priori relation to subfactor theory. But it turns out that subfactor theory gives a very powerful tool to study quantum field theory and conformal field theory particularly. So I'd like to talk about such a relation between the two theories, and then the theory of tensor categories plays an important role in this connection. So I start with subfactor theory, but before going into subfactor, we just look at the factor, which was already defined in the talk of Dave. But then he basically talked about the finite factors. But then in the setting of conformal field theory, we almost never get finite factor. So what we have is so-called type 3 factor. So I start with some basic explanation about type 3 factor. Then for simplicity, I assume that all Hilbert spaces appearing in this series of lectures are separable. So I consider only separable Hilbert spaces. In this way, we can avoid some technical subtleties. So we consider only. So we all from algebras are assumed to act on the separable Hilbert space from the beginning. Then, of course, there is a standard definition of a type 3 factor, but I take a rather simpler form. So I take this definition because of this assumption which makes the thing simpler. So, a von Neumann algebra M is called a type 3 factor if any non-zero projections are equivalent. E and F are equivalent. That is, there exists some partial asymmetry U in M such that U star is E and U star U is F. And actually, the trivial example of the complex number field satisfies this condition, so we have to exclude this. And it is not one-dimensional. So in this way, we can define a type 3 factor, but then from this definition, it's not clear at all that such a von Neumann algebra exists. Because, so, for example, in the case of finite von Neumann algebra, as they've explained, this never happens. So, I start with some examples satisfying this property. So 6 a real number lambda between 0 and 1. Then we take a state on M2C, that 2 by 2 matrix algebras. So for 2 by 2 matrix algebra, we take a product with this 2 by 2 matrix, a diagonal matrix, and then take a standard trace, normalized. Then, so this is a state on the 2 by 2 matrix algebra. Then we look at the infinite tensor product. So consider infinite tensor product of and we can make sense of this infinite tensor product as a certain fifth algebra, which is a closure of the union of finite tensor products. And so this makes sense. Then take a GNS representation, which appeared in the talk of this. So this is the fifth algebra A. Then we can take the algebra phi of A double commutant. So this is a von Neumann algebra by definition. Then this is a type 3 factor. This is the so-called power factor.
What is n in the tensor product there?
So we just take the infinitely many copies of the same state on the same von Neumann algebra. So n is just the index.
It's an index, but it's not. There's no dependence there.
That's right. There's no dependence on n. Yeah. We just take the same one infinitely many times. This is the so-called power factor, and it's not trivial at all to prove that this really satisfies this condition. But some heuristic argument is the following. So in a 2 by 2 matrix algebra, just one copy, then so this these two projections are equivalent in this sense because take 0, 1, 0, 0, then u star is one of the two, and u star u is the other one, so they are equivalent. But in that state, so that state gives a certain way of measuring the size of projections. But with the values phi lambda for these 1 over 1 plus lambda and lambda over 1 plus lambda, so they are different. So it means that so we have two projections of different size, but they are equivalent. So in this way, in this system, we somehow mix the size of projections. I mean, different projections of different sizes are equivalent in this way. So somehow the different projections of different sizes become equivalent in this setting, then all difference between the size of projections disappear in the limit procedure. So, so projections of different size are equivalent. So this is some rather naive heuristic argument whether why we should get this type of property. And so I took lambda between 0 and 1, but if lambda were to be equal to 1, then that trace is 1/2. So it means that the normalized trace. And in this case, these two projections are the same size. Then in this case, we get a factor, a finite factor, actually. But now lambda equals 1 is excluded, so we get type 3 factor. So this is written as R sub lambda depending on lambda. And actually, if lambda the different, we get a different fundamental algebra, but not trivial at all. Then choose lambda and mu in this interval is log lambda over log mu are irrational. Then we have two power factors are lambda and r mu. Then under this assumption, we have a natural notion of a tensor product of von Neumann algebras, and then this is unique. This tensor product is unique up to isomorphism. Again, this is not trivial at all, but we can prove this one. And
so you mean unique, like no matter which lambda and mu you took, as long as
this
is irrational?
Yes, that's right. We always get the same von Neumann algebra. Yeah.
What are you gonna if the quotient is rational?
Then if this is rational, we get one of this for other value of lambda.
So you're saying, this is always the same denominator, or they're always different? Sorry.
Always the same.
It's the same, as long as this
Okay.
condition.
What is it?
It's the 3-1.
Yeah, 3-1. So this is called the hierarchy. This factor of type 3-1.
So did Lackey was prove this thing?
Yeah, right, actually, they proved this uniqueness.
What happens if I do the same construction but I have a sequence lambda n?
That's
That's actually what
that's
they
what
did.
that's what they
Yeah,
used to have the idea of the
Yeah.
asymptotic
that's right.
ratio.
So what's the answer? Is it? I mean,
So it depends on the sequence lambda n, but so basically this one or one of them also we have another possibility.
And how do I if I give you a sequence lambda n, how do I determine? which
Well, it's
one I get?
complicated procedure called asymptotic ratio test. So actually, in this example we took 2x2 matrix algebra, but we can take also n by n matrix algebra. So we have a sequence of that eigenvalues, and then from this sequence we can determine a certain asymptotic ratio set, and this determines the isomorphism, basically the isomorphism class of the infinite tensor product from the algebra. Yeah, that's what Lacan did many years ago. So, but I particularly singled out this example because this is a von Neumann algebra which appears in conformal field theory. So we always get this von Neumann algebra. So it's enough to consider only this, just one example of von Neumann algebra in order to study conformal field theory.
Can you give an example in conformal field theory where it shows up?
Well, that's rather complicated. So I'll talk about that later, maybe on Friday, or maybe at the end. Yeah. Then I'll make a very short explanation of the Tomita-Takesaki theory for this setting.
Is there a notation for the standard notation for the afterwards?
Oh yeah, sometimes I feel so.
Sorry, what do you get if it is rational? If the ratio is rational, then what is?
Well, so it's what's it's rational. It's log of nu to some integer power, and we take the smallest or largest of such nu that type 3 nu.
That's one of the powers.
Yeah. In a very short form. So let's M be a type 3 factor. Maybe this one. Acting on several Hilbert space H. Then actually we can, in this setting, we can always find a so-called cyclic separating vector omega, that is, if we apply this from the algebra M to omega, this is the dense subspace of H. And also, if we apply M prime the commutants to this single vector omega and then take a closure, then we get the entire Hilbert space. So that so we take such omega, and actually we can prove that we can always find such a vector omega in this setting. So take.
So you're saying anytime you have a 3-1 factor represented on H?
I mean,
is this
type 3 factor.
type 3 factor?
Yeah. On a separable Hilbert space, this is always possible. Then we consider an operator S0 sending x omega to x star omega for any xi in M. And actually this is a well-defined operator, densely defined operator by this property. And actually this operator already appeared in the talk of Dave, but here the one thing that, so we want to take the closure with 0, and this is possible, but this is always unbounded. So this is only a densely defined closed operator. So that's different from the finite case, which Dave explained. Then we have, and actually this is an anti-linear operator because we have star operation here. This is an anti-linear operator. Then we still have the machinery of the polar decomposition. and then this is this one. J, then actually, so this is anti-unitary part. And actually, and this is a positive part. And then it turns out that we have J where is identity. So this is the modular conjugation which also appears in the talk of Dave. But now in the setting of Dave, this delta part doesn't appear. This is the identity operator. But here we have some this unbounded. So then we have this one, and then we have this switching of M and M prime and the joint action of the J operator, which already again appeared in the talk of Dave, but now the setting is different. But still we have the same identity for this J. And also from this delta, so this is a real number. So if we take so delta is a positive operator, actually non-singular. So we can take a power to the it for real number t. Then this is a unitary operator. And if we take a joint of this unitary operator acting on M, then we get the same algebra M. It means that for any t, this gives an automorphism of the von Neumann algebra M. And this gives a one parameter automorphism group acting on the von Neumann algebra M. And this contains a lot of information about the structure of M, and that's an important ingredient of the Tomita-Takesaki theory and also the common classification in 70s. But for the conformal field theory, this delta part is not so important. It has some significance, but not so particularly important. And this J part is more important. So we can switch the M and the M conjunctant in this setting.
How much do these things depend on the representation?
Oh yeah, this depends on so this depends on the choice of omega. But okay, I should. But somehow the dependence on omega is small. Omega is small assumption. So basically we can ignore the dependence on omega. It's almost the canonical thing. Just depending on M itself. Then this is about a single factor. And now we come to a subfactor. So by definition, a subfactor means von Neumann subalgebra N containing M and where N and M are both factors. In this case, we say N is a subfactor of M. So this is the setting of subfactor theory. And under the natural setting, so both are finite or both are both are type 3. And so in this series of lectures, I'm interested in this latter case, but for some explanation, I start with this finite. So in this setting, we want to define the Jones index. And this definition hasn't been given the episode yet, so I start with this finite definition. So, so finite case, we consider this, so we have a trace, then we have the Hilbert space L2M, which I explained by Dave. Then, so he talked about bimodule, but also we can just consider one of the two actions, only the left action. Then this is clearly a left n module. Of course, we have a left action of M itself, the large algebra, but we can restrict the left action to be the small algebra. So then we have this is a left n module. So we have the right action, but we can ignore this one. Then it turns out that this is always of this form. As a left n module, this is always isomorphic to this. So where Pi is a projection in N. So for one copy, we take L to N, which is the Hilbert space arising from the GNS construction of N, and we take a projection in N, and if we have a right multiplication of Pi to this copy, this still has a left action of N. So this is, and also this is the Hilbert space. So this is a natural left n module. This is, so we always have this isomorphism. Then the definition is one of the possible definitions is that the Jones index. So we have this, so we measure, basically we measure the size of this left n module. And we measure each left n module by the size of this projection, which is given by the trace value of this projection. And actually this is very defined. And from this construction, it's not trivial, but this is very defined. So this is basically the definition of the Jones index. And yeah, so this symbol is similar to the notation of the index of a subgroup. So if we have a group and subgroup, we have notion of the index, and somehow this is similar to that situation. So instead of groups, we have an algebra and subalgebra, and then we have something like the index. Well, this is still called the index. So this is the definition of the Jones index. And this is value. So n is contained in M. So in a sense, this is contains L to N always. So it is at least we have one copy of L to N. So this we always have at least this value. So this is a real number, and at least the value is 1, and also possibly infinite. So this is a general thing. But for the case of infinite index easily occurs, but that's a technically complicated situation, and we are interested in finite index case. So we usually assume that this index is finite. And the typical example is the following. So let n be a finite factor, for example. And m is n tensor n c. So this is an algebra of n by n matrix algebra with entries in n. So this is a tensor product. So that's the thing. Then in this situation, so the n times the identity matrix is contained in n. So in this sense, this can we can regard that this is a subalgebra of M. This is regarded as a subalgebra. So in this case, from a naive viewpoint, this M contains n squared copies of n. So that's actually the value of the index. So this is the easiest example. So, from this kind of the easy construction, we can see that these Jones index values take values of square integers. But then other values are not clear at all to realize. Then the next example is another example. M, the larger one is a finite factor, and G is a finite group, and alpha is an action of this finite group G, an automorphic action acting on this M. Group homomorphism from G to the automorphism group of M, and that we assume that alpha G is not inner automorphism, which is of this form. So if we have this is a unitary operator, the set of unitary operators on the factor M. So if we take a unitary operator joint view, this gives a automorphism of M. But they are rather trivial type of automorphisms, and we use the symbol int of M to denote the set of inner automorphisms. They are inner automorphisms. So they are rather trivial type of automorphisms, and we assume certain non-triviality. That is, so this is the identity element of the group G, and of course for one we have the identity automorphism which is inner, but for other group elements we assume that the action, the automorphism is not inner. And actually, if I use a certain typical Pontryagin algebra, we can always realize such an action for any finite group G. Then, in this station, we look at a fixed point algebra, which is the subalgebra of all fixed points by this group action. Then this is also a factor. And the Jones index is So then the Jones index, this subfactor is now the fixed point area, and then this is equal to what? So the only some natural number appearing in this setting is the order of this finite number. This is indeed the index value. So this is a typical example. This is not so trivial to see this equality from the definition, but we can prove this.
Sorry, can I ask, you said you can always find such an action, is that, I mean, when M is
It dep-
divided
it
to one
de-
factor, or for any M?
It depends on M. If this is an arbitrary to one factor, such an action may not exist for some G.
Okay.
But for typical finite factor appearing from the infinite tensor product construction, this is always possible for any finite.
So it could be that instead of the order of the group, you have some divisor of it.
Well, we always get the order as long as this non-triviality assumption of the action. So,
But it's possible to have two one factors with no outright automorphisms, right? So this is the comment that was being alluded to.
so this is one thing. So from this, so we can realize any integer value as the Jones index value, and which is somehow similar to the index value of the subgroup in a larger group. But then other values, other non-integer values, it's not clear at all whether they are realized as a Jones index value or not. But the first breakthrough to Jones in early 80s, but the possible effect of this effect. So 4 cosine squared pi over n, and up to, so the n is an integer starting from 3. So for the first value, n equals 3, so we have cosine pi over 3, which is 1/2. So squared times 4 is 1. So the first value of this series is actually just 1. The next value is for n equals 4, we have cosine of pi over n, which is 1 over square root of 2. So the square is 1/2. So times 4 is 2. So the first value is 1, the next value is 2. Then the next value for n equals 5 is somewhere between 2 and 3.
This is still finite.
Yeah. Yeah. Then the next value for n equals 6, then pi over 6 and take a cosine, that is square root of 3 over 2. So the square is 3 over 4 times 4 is 3. So the next value is 3. And then the next value is somewhere between 3 and 4. And then as n goes to infinity, this cosine part goes to 1, approaches to 1, and so we have a multiplication by 4, so we have certain values converging to 4. And then after that, any value is possible. Up to infinity. So this is the picture of the set of possible values of the Jones index. So this is, so actually for this part, his construction is rather simple, but for the values below 4, so this, so impossibility of the other values and also possibility of these values are both non-trivial, highly non-trivial, but this was first proved, found and proved by Jones. Then So, and that, so now up to this point, everything is about finite factor. And now take factor of type 3. So now both n and m are type 3 factors. And in this situation, we want to define the index. But this definition of the index which already disappeared. But that depends on the structure of left module, and actually that depends on the trait. And actually, the trait appeared in the definition. So in this station, we have no trait, so we cannot imitate the definition of that of the index in this situation. We have to do something else. Then, okay. Before this, I should start. Sorry. So, still finite. Finite case, we have a notion of conditional expectation. So, suppose we have a finite subfactor, subfactor n in M where both are finite factors. Then we have okay. We have L2 of M, which arises from the completion with respect to the inner product arising from the trace. And also we have L2 of N. And then this is a natural Hilbert subspace of L2 of M. So we have a Hilbert space and a subspace. So we have a natural orthogonal projection. Then this, sorry. L2 of M is a completion of M, so it contains M, and also this contains N. And then we restrict this projection to subspace sorry, M. Then it turns out that this actually maps into M. So, and this is the conditional expectation, and we have the following property. So E is a boundary linear map. Maybe not trivial, but E is we have following. If we apply E twice, then the effect is the same as 1E. So we have this property. And also, this E is a norm decreasing map from M to N. So we get the following. Then, so in general, such a map is called a conditional expectation. And this name comes from probability theory, classical probability theory, because in the classical setting, so commutative von Neumann algebra is actually L infinity function algebra. Then the subalgebra corresponds to sub-sigma algebra on the same space. So it means we have a larger von Neumann algebra and smaller von Neumann algebra. In the commutative setting, it means on the same space we have a larger sigma algebra and smaller sigma algebra. Then for the larger sigma algebra, measurable function is not measurable in general with respect to the smaller sigma subalgebra. Then we have this kind of map from a larger algebra of measurable functions to the smaller algebra of measurable functions. That's a natural property and this type. And in classical probability theory, such a map is called conditional expectation. So that this is a generalization of such a classical notion. Then Kim's and Popper prove the following. So the set of lambda, non-negative integer, non-negative real numbers, for all positive elements with m plus, positive elements of m, we assume this inequality, this operator inequality, E of x is larger than or equal to lambda times x. And then we look at all possible values of lambda, satisfying this property. Then there is soup of such possible values of lambda, and then this is equal to the inverse of the Jones index value. This is one characterization, and actually this could be infinite. So we set the inverse of infinity is 0. So it may happen that this is possible only lambda equal to 0. In that case, that happens exactly when the Jones index is infinite. So this is one characterization of the index due to Kim's Popper. So based on this, we want to make generalization of the Jones index type 3 extension. So now, so we look at the type 3 subfactor, and then there may or may not exist such a conditional expectation map E in that sense. So the abstract definition of a conditional expectation means that we have these two properties, the square. So E is an idempotent and also the norm 1 map. So this is an abstract definition of conditional expectation. So as I said, such a map E from M to onto N may or may not exist. But if it exists, then we can define index of E by that formula. So soup. This formula makes sense without trace. So soup, we take a soup, supremum and inverse. And this is the index value of this conditional expectation. So depending on the conditional expectation, we have this E. Then, if such me this. Then there exists a conditional expectation minimizing the index value. So this is due to here in the early days of subfactor theory. So if we have if we have a conditional expectation from M on to N, then there is some actually unique conditional expectation which minimizes the index value of the conditional expectation. So we set this value to be the Jones index. And if we don't have a conditional expectation from the beginning, then the index is defined to be infinity. Yeah, if we don't have conditional expectation, in a sense, the smaller algebra n is too small with respect to m. That's an interpretation of non-existence of conditional expectation. So in that case, we should set this to be. And one important remark is that in a typical situation, we have the so-called irreducibility assumption. If we have so the commutant of the small algebra in the large algebra, this can be C. This never happens in a non-trivial situation in a finite dimensional situation, but this often happens infinite dimensional factors. Then, from the beginning, the conditional expectation is unique, if it exists. So this is a typical situation, and in this case, we don't have to take this. We don't have to consider this minimization because it's unique from the beginning. So in this case, we have a unique conditional expectation, and by this formula, we can define the Jones index. And we still have we have still the same set of possible values.
How do you show, what's the method used to show this uniqueness if it exists? So in the reducible case, is it some form of Dix-Meyer averaging?
Yeah, kind of. Yeah. In a general situation, we have a certain formula for conditional expectation depending on some choice from this subalgebra. But there we have, for this irreducible case, we have no choice for such a situation. Then we will get uniqueness of a conditional expectation. So we still have the same set that is 4 cosine squared pi over n and the interval for infinity, including the infinity. So this is the setting of Jones index theory for type 3 subfactor. Then, I don't have much time today, so I just have the setting for bimodule.
So could I just ask this restriction on the possible values, is that the actual possible values of
Yes.
the index of a conditional expectation?
Yes.
Or just the index of the subfactor?
Both. Yeah. Yeah. For the setting, so we already saw bimodules in the talk of Dave. So bimodule theory is very important for study of subfactors. So we have some natural appearance of bimodules. So in the remaining time, I just introduced standard bimodule, the trivial bimodule for M. So M is the now type 3 factor. On H with omega, this cyclic and separation. Then this Hilbert space H is a natural M bimodule. So we have the left action and the right action. The left action of M is the original action of M itself, but so we want to define the bimodular operation. So for any Xi in the Hilbert space, we have the left action of X and the right action of Y, and this is defined for X part. We just multiply X, but for this part, we have this operation. So this is J is the modular conjugation operator. So in this way, we can define the right action of M, and this gives something intermittent here. So this X and this part commutes. So we have the left action of X and the right action of Y, which commutes on the same Hilbert space H. So this gives a M bimodule structure. Then starting with this, we will consider more general bimodules for type 3 factor M. So I stop here today.
Great, thank you very much. Any more questions?
Yeah.
So for type 3, you can also find index using Longwith's approach, right? That if the inclusion map from N and M has a dual map,
Yeah.
and then, so that approach, that's certainly much easier to state, right? Is there an advantage of this conditional? It's easier to prove things using conditional expectation.
For proving something, I think this doesn't have a particular advantage, but just in defining the index is probably the easiest in this approach. That's what I thought.
What is the?
So you can look at the inclusion map from N into M. So finite index essentially just means there should be a dual map from M to N, such that it behaves like a dual. When you compose them, it contains the identity.
Yeah, right.
And then the index pops out as a scalar in the duality.
Yeah, right.
So from the point of view, that's I think
Yeah,
easier.
that's kind of a categorical approach.
I mean, yeah.
Yeah.
I mean,
With sectors as well.
Section or
what's that?
a section?
This is Longwith's approach, but I mean, I just feel like it's easier to, I mean, this approach is sort of, you have to talk about the existence of conditional expectations and possibly multiple expectations and a minimal. Whereas in that case, it's just essentially the existence of a dual thing.
Yeah, that's right.
I guess maybe identifying the scalars may be a little more involved that way.
Yeah.
Whereas saying whether something's finite index seems a bit easier in that sense.
Yeah.
But with the expectation definition, you can write down a simple example of one matrix.
Yeah,
inside
that's
of
right.
it.
Yeah.
So it's computationally more.
Yeah.
So you
So I
do some very simple
Yeah, that's right.
exercises.
I gave example of tensor product with finite matrix algebra and also group fixed point algebra application. And with this definition, we can write down the conditional expectation explicitly. So that's gives some easier computation.
But the dual picture will come out when
Yeah.
you do the binaural
Yeah.
picture.
Yeah.
Any more questions or comments? Okay, so thanks again.
Thank you.
Meet again tomorrow.
Yeah.
Let me ask Yasu, in your monograph with Marcel Bischoff and Longo and Raring,
Yeah.
do you do alpha induction from I know it's very diagrammatic, and so you
Yeah.
will, do you talk about alpha induction in there from
No,
a diagrammatic
not really.
perspective? Do you know a reference for the categorical diagrammatic expression for alpha induction?
I think our first paper is still
That's the canonical
Yeah.
reference
Yeah,
for
yeah.
alpha induction. Probably it's on the monograph. You can look at, so this is the Kawahigashi paper on alpha induction.
But that's from a subfactor.
That's from the subfactor.
Yeah.
You can just look at it and
Try and
just
understand.
write it down. Braiding tensor category.
You'll see all right.